Hey guys, I'm Perry from Math Together Canada. Welcome back to our problem solving series. This is the final video in our 2024 Euclid solution presentations, and today I'll be doing problem 10 for you guys. Keep in mind that this is the final and hardest problem on the entire contest, and let's dive right in.
This is problem 10 of the 2024 Euclid. In this problem, we're given some coordinates that form a triangle and some points on the sides of these triangles that partition the triangle into 4 regions of equal area. And the numbers such that this is possible are called balancing pairs. All right, let's first look at 10a. So in the question, we're given points A, -1, 0, C, 1, 0, and B, 0, 4. We're also given points S and T on AC, and we then have Q and P such that these 4 regions all have the same area. Now, in this problem, for part A, we're given S is equal to 1. This means that S is equal to 1, 0, which is actually equal to C. So we can update our diagram here. I'm going to erase some parts of this. So S is now actually there. So all of these 4 regions have the same area. First, we can calculate the area of ABC. ABC is equal to, since AC is 2 and the y-coordinate of B is 4, the area is 2 times 4 over 2, which is just 4. Therefore, each of the small regions has area 1. Now, this gives that area of APC is equal to the area of BPC is equal to 2, since each region consists of 2 of the small regions. But since APC over BPC is equal to AP over BP, since the 2 triangles have bases on the same line and the same upper vertex, so that area ratio is just the ratio of their bases. But we know that these 2 are both equal to 2, so this is actually equal to 1. This means that AP is equal to BP, so P is the midpoint of AB. Therefore, the coordinates of P are just -1 plus 0 over 2, 0 plus 4 over 2, which is equal to -1 half. Sorry. -1 half 2. Alright, moving on to 10b. We're asked to prove an equation of this form for every single balancing pair S, T. So I'll draw a bigger diagram here. We know that from our work in part A, the total area is 4, so each of these small regions has area 1. The question gives that S has coordinate s comma 0, this has coordinates negative t comma 0, where s and t are both positive. Thus, this length is s and this length is t. Let's call the point where SP and QT intersect x. Then we're going to let P have coordinates xp, yp. Q have coordinates xq, yq. And x have coordinates u and v. Now, what do we know? We know that the area of triangle STX has to be equal to 1. The base is ST and the height is going to be V. Therefore, 1 equals STX is equal to S plus T times V over 2, which gives that V is equal to 2 over S plus T. We also have that 2 is equal to the area of APS, since it's consisting of this one and this one added together. This is going to be equal to, call the origin O, since AS is going to be AO plus OS, which is S plus 1, that's the base, and the height is going to be the y-coordinate of P. This gives that the y-coordinate of P is equal to 4 over S plus 1. By symmetry, we also have the y-coordinate of Q being equal to 4 over T plus 1. Now we can find the equations of lines AB and AC. They pass through points A, B, and BC, which we already know the coordinates of. Note that since AO is 1 and BO is 4, line AB has slope 4, and the y-intercept is just B. Therefore, AB has the equation y equals 4x plus 4, while BC has the equation y equals negative 4x plus 4. We can now plug in these y-coordinates into these equations to solve for the coordinates of P and Q. We get that P will be equal to, well, the x-coordinate of P is going to be equal to y minus 4 over 4, since it lies on line AB, which is going to be equal to, if we plug this in, becomes 4 over s plus 1 minus 4 over 4, which is equal to negative 4s over s plus 1 over 4, which is equal to negative s over s plus 1. Thus, P has coordinates negative s over s plus 1, 4 over s plus 1. Similarly, we can do the same calculation for Q. We already know the y-coordinate of Q, and since it lies on line BC, we must have that the x-coordinate is equal to negative y minus 4 over 4 equals negative 4 over t plus 1 over 4. No, wait. These should be positive sign. over negative 4. In the end, we get that Q should be, this turns out to be 4 over, sorry, not 4, t over t plus 1. So we get the coordinates of Q to be t over t plus 1, 4 over t plus 1. But we still don't have an equation to figure out or to relate s and t. So therefore we need to look at triangle STX, particularly point X, which is the intersection of lines SP and TQ. Since we know the coordinates of S and P, we can calculate the slope between the line. S is S, 0, P is negative S over S plus 1, 4 over S plus 1. The slope between these will be M is equal to 4 over S plus 1 over negative S squared plus 2S over S plus 1, which is equal to negative 4 over S squared plus 2S. Since this line passes through S, 0, we have the equation of line SP, which is going to be y equals negative 4 over S squared plus 2S times X minus S. We can move the denominator to the other side to get that S squared plus 2SY is equal to negative 4X plus 4S. Similarly, we get that line TQ should have equation y equals 4 over t squared plus 2t times x plus t, which is equivalent to t squared plus 2t y equals 4x plus 4t. Now, what do we know about x? We know that x is going to be the solution to this system of equations right here. Additionally, we know the y coordinate of x, which is v. Thus, u comma v is the solution to this system of equations. And when we add these two equations, we get that s squared plus t squared plus 2s plus 2t times, in this case, y is going to be v, since it is the solution of both. These two cancel. This is going to be 4s plus 14. However, earlier we had that v was equal to 2 over s plus t. When we substitute that in, we get s squared plus t squared plus 2s plus 2t times 2 over s plus t is equal to 4s plus 14. And this is the desired equation we want between s and t. Once we move the piece in the denominator to the other side and simplify the equation, we can divide by 2 on both sides. Expanding gives s squared plus t squared plus 2s plus 2t equals 2s squared plus 4st plus 2t squared. And this gives s squared plus t squared equals negative 4st plus 2s plus 2t. If we look back at the equation form they want, that's the form they wanted. And so we get d equals negative 4, e equals f equals 2, and g equals 0. Okay. Finally, for part 10c, the only thing that matters is this equation that we found. We want to find an infinite family of distinct pairs of rational numbers st that is a solution to this equation, satisfying zeros. Satisfying, what's the condition? 0 is less than s is less than or equal to t is less than or equal to 1. Okay. What we're going to do is we're going to, since s and t are both rational numbers, we're going to let k equals t over s so that t is equal to ks. Note that since t is at least s, we have that k is going to be greater than or equal to 1. Substituting this into our equation above gives us s squared plus k squared s squared is equal to negative 4k s squared plus 2s plus 2ks. Since s is not equal to 0, we can cancel a factor of s from every single term to get the s plus k squared s plus 4ks is equal to 2 plus 2k. This gives that s is equal to 2k plus 2 over k squared plus 4k plus 1. Since t is equal to ks, we get that t is equal to 2k squared plus 2k over k squared plus 4k plus 1. So we get the infinite family of solutions 2k plus 2 over 4k squared plus, not 4k squared, k squared plus 4k plus 1, 2k squared plus 2k over k squared plus 4k plus 1. Now, it would appear that this is a solution to the problem, and we're done. However, we still need to verify that, why did it jump? We need to verify that this condition holds. Now, we've already checked s is less than or equal to t because we force k is at least 1. Now, additionally, since k is positive, we see that s here is also clearly positive. So the remaining condition is t is less than or equal to 1. Then we need that 2k squared plus 2k over k squared plus 4k plus 1 has to be less than or equal to 1. Since the denominator is clearly positive, we can multiply both sides by k squared plus 4k plus 1 without changing the inequality sign. This gives 2k squared plus 2k equal to k squared plus 4k plus 1. So we need k squared minus 2k plus 1 is less than or equal to 2. This is equal to k minus 1 squared is less than or equal to 2. Since k is at least 1, this piece is positive, so we can take a square root to get that k is less than or equal to 1 plus root 2. Therefore, we have the bound of 1 is less than or equal to k is less than or equal to 1 plus root 2. Since k can be any rational number, since it's the ratio of two rational numbers, we do indeed have infinitely many rational numbers in this range. However, there's still one more thing we need to check. We need to check that this family actually is infinite. For example, if we just had the set 0, 0 for k is any integer, k can be any integer, but this family is clearly not infinite because it only has one element. So what we can do is we can suppose that there are two different values of k, say K1 and K2 such that the S values are equal. Then we have that 2K1. Now, if the S values are equal, but K1 and K2 are distinct, then what do we have? Then we note that T is equal to K1S. Well, T1 will be K1S. And T2 will be equal to K2S. But then since K1 and K2 are distinct, this forces T1 and T2 to be distinct. Therefore, if the value of S is the same, the value of T is not the same. And so we find that every value of K will give a different solution for S comma T because the ratio of T over S is unique. Therefore, the infinite family of 2K plus 2 over K squared plus 4K plus 1, 2K squared plus 2K over K squared plus 4K plus 1 for rational K in 1 plus root 2. This infinite family indeed satisfies the problem constraints. Therefore, we finish 10A, 10B, and 10C. And that's the end of our Euclid solutions. Thank you.
Alright, and with that, we've made it through the entire problem. If you have any questions or suggestions, always feel free to drop a comment below and we'll answer right away. Please subscribe to our channel to stay updated with our videos and to support our channel. Thank you again, and have a great day.